Now, finally, our promised shortcut, the rule for differentiating powers of x. So if f of x equals x raised to some power, then the derivative, f dashed of x, is n times x to the n minus 1. In other words, we multiply the n down the front and we subtract 1 from the power. And that's it. That's the rule that we have at the moment. If our function is the sum of two other functions, then the derivative is the sum of the derivatives of those two functions. And if our function is a constant multiplied by some other function, then the derivative is the constant multiplied by the derivative of that function. These other points, to find the points where the tangent has a given gradient, they just need us to be very sure about our language. So the tangent has a slope which is the same as the value of f dashed of x. And at a particular spot, that slope will have a particular value. So we solve this equation. We solve f dashed of x equals whatever it is we want the gradient to be. And finally, to find the y-coordinate of a point, we know we substitute back into f of x. Now, none of this is tricky, but it's going to be presented differently. So we just need to be comfortable about how we operate this. So I'm going to do a selection of examples. So for our first one, if f of x equals x to the 7, then f dashed of x is multiply the power down, subtract 1. So it's 7x to the 6th. If f of x equals 9x to the 5th, f dashed of x is multiply the 5 down, so 5 9s are 45, and subtract 1 from the power. When we've got a constant, then f of x is equal to 0. And the reason for that, not that we have to stop and think about it, is that what we've really got sitting here next to every constant is x to the 0. And when we multiply that 0 down, that gives us 0. We don't have to go any further. Okay, for this one here, use the rule to find the derivative and then find f dashed of 0. So we're just going to do that for one of these. So for this one here, the derivative is, so f dashed of x is, twice 3 is 6, and take 1 from 2, minus 5. So this is our derivative, and therefore the derivative at 0, which means the slope of the tangent, which is the slope of the curve at 0, is 6 times 0 minus 5. So it's just minus 5. Okay, now for these next few examples, again I'll just do a couple of them. We saw up above that we have a way of taking the derivative of a single term, and we have a way of taking the derivative of two terms added together, or of a term multiplied by a constant. But as yet, we don't have a way of dealing with something like these here. We will, but for the moment we don't. So if we have something like these, which are products, so they're two terms multiplied together, then we have to resolve that product first. So for example, this one here, we just have to do our expansion of brackets. So we've got an x squared plus 4x minus 2x, so that's plus 2x minus 8. And then we've got separate terms being added or subtracted, so we can apply our rule. F dashed of x is then 2x plus 2. For this one over here, again it's a product, it's a 7 minus x times 7 minus x. So we can easily work that out as square of the first minus twice the product plus square of the second. And then it's in the form where we can apply our rule. So the differential of this is 0, the differential of this is negative 14, and the differential of x squared is 2x. So we'll just do this first one here. So part A says find the derivative of that. So f dashed of x equals, by our rule, 2x plus 1. Part B says evaluate f dashed of 0. So when we put 0 into this, we'll get twice 0 plus 1, which is just 1, to show that the tangent at this point, 0, 1, has a gradient of 1. So we've shown that the gradient when x equals 0 is 1. I guess we really should show that when x equals 0, y is 1. How do we do that? Well, the y value is what we get when we put the x value, which is 0, into our equation, our original equation. So that'll be 0 plus 0 plus 1. So we've done everything we need to there. Part C, solve tan alpha equals 1 to find the angle of inclination of the tangent at 0, 1. So we've just found that the slope of the curve and the slope of the tangent are both 1. We know that gradient equals tan of the angle of inclination, so therefore tan of alpha equals 1, and therefore alpha is the angle whose tan is 1, which will be 45 degrees. Okay, so now we need to add to our list of tools for finding the derivative. So we've seen what to do when we've got x to the n, what to do when we've got terms added, what to do when we've got terms multiplied by a constant. Now what do we do when we've got these quotients, or in other words, terms to a negative index? So let's go from first principles. F dash of x will be the limit as h tends to 0 of f of x plus h, which is 1 on x plus h, minus f of x over h. And if we then do what algebra suggests that we do, we get a common denominator for these two fractions up the top. So our common denominator on the top would be x outside of x plus h. That will give us x plus h will go into this x times, so it will give us x minus, and x will go into x plus h x plus h times, so minus x plus h all over h. So when we look at this, it takes longer to write to do anything else. Our top line here is x minus x, so that's gone, and minus h over x times x plus h, that's all over h. Now, depends how you think about fractions, whether you want to invert and multiply, or whether you are just happy to cancel that out, but that's what we're doing. So we want the limit as h tends to 0 of 1 on x outside of x plus h. And now we can substitute the value of h equals 0 into there, and we just get minus 1 on x squared. Now, how does that stack up with our rule from before? Well, remember, f of x equals x to the 1 on x, it's also x to the minus 1. So our previous rule said multiply that number down, which would be minus 1 times x, and subtract 1. So that would be x to the minus 2. And x to the minus 2 is x squared on the bottom, so it's minus 1 on x squared. So what we've established is that for negative indices, then our rule from before works exactly the same way. So we'll just do a couple of these. Say when f of x equals 1 on x squared, then if I rewrite that as x to the minus 2, then f dashed of x will be minus 2x to the minus 3, and it would be nice to put that back into the form it was originally, which is just that. Now, down below here, it's a bit more complicated because we've got things being multiplied and divided. So all that we can really do, again, is simplify algebraically to start with until we get a better rule later on. So if we do the middle one here, if y equals these things, then it means it equals 5x to the 6 over 3x cubed, and it equals 4x to the 5th over 3x cubed. So we could break it up into two terms. So if we do that, then we'll have 5x to the 6th over 3x cubed plus 4x to the 5th over 3x cubed. Now those 3 will go out with 3 of those. Those 3 will go out with 3 of those. So that means that we've got 5/3 x cubed and 4/3 x squared. So that at that point, when I find y dashed, I just apply my usual rule. So 3 lots of 5/3 will just be 5, and I subtract 1 from the power, and 2 lots of 4/3 will be 8 on 3, and I subtract 1 from the power. Okay, so now what do we do with fractional indices, like f of x, which is root x, which we know is x to the half? So we're just in the process of checking our shortcut, basically. So we go back to first principles, and they say that we would want f of x plus h, which is square root of x plus h, minus f of x over h. Now, where we go from here is again a little bit more of algebra informed by your past experience. So when we did surds and we used the technique of rationalizing the denominator, then we're going to use a similar technique to that here. We're going to multiply top and bottom by the conjugate. So we'll do this. And then when we do that, I've got the limit h tends to 0, we can't leave that bit out. Our top line becomes the difference of two squares. It becomes square root of x plus h all squared, which is of course x plus h, minus the square root of x all squared, which is of course x, which then just leaves us h. Down the bottom, we've got h outside of square root of x plus h minus square root of x. And you can see that this h and that h will cancel. So we have the limit as h tends to 0 of 1 over square root of x plus h minus the square root of x. Now at this point we can put h equals 0 in here and we won't have a problem, and our bottom line will then just be a root x plus a root x. That looks a little bit better. Root x plus root x, which is 2 root x's. Now if I rewrite that in index form, that becomes half x to the minus a half. Compare that with our normal process from up here, where we would say f dash of x we find by multiplying the power down and subtracting 1. So a half minus 1 is minus a half. So by differentiation from first principles, we've verified that our rule also applies to fractional indices. Okay, nearly there. Let's just do, say, this example here. So y equals the 4th root of x, which means that y equals x to the quarter. So y dashed is 1/4 x to the minus 3/4. And if I wrote that back in surd form, my quarter sits here. The x is going to be on the bottom because of the negative. We're going to be taking the 4th root and we're going to be cubing it. Okay, bit messy, but good enough. Okay, now last example before you get on and do problems. Part A, show that the derivative of y equals 4 on root x is that. So 4 on root x is 4x to the minus a half. So dy dx, which is another notation for differential, the derivative, as is y dashed, it's a shorthand. So dy dx is, bring this down, so that'll be minus 2x to the minus 3 on 2. So here, that's going to give us this negative, and the 2 up the top, and x to the 3 on 2 down the bottom. Now what is x to the 3 on 2? Well, x to the 3 on 2 is, well, let's write it first. X to the 3 on 2 is the square root of x cubed. And if we have the square root of x and it's cubed, then this is root x by root x by root x, and a root x by a root x is x. So it's minus 2x x times root x. Takes longer to say than do. Okay, find the equations of the tangent and normal to the curve at the point where x equals 4. So, what is it that we've just found here? We've found the slope of the curve at any point on the curve. So, if we find y dashed when x equals 4, then what we're doing is finding the slope of the curve where x equals 4. So that will just be minus 2 on 4 root 4, which is going to be, so this will be cancelling with that, it's going to be minus 1/4. So the slope of the tangent, or the slope of the curve, same thing, is minus 1/4. And it's at the point where x equals 4, and we're after the equation of the tangent. It's a straight line. The equation of any straight line we know well and truly by now is given by that. What's the y value when x equals 4? Well, we have to put that value of 4 up into here, our original equation. So 4 on root 4 is 4 on 2, which is of course 2. So y minus y1 equals that, minus 1/4 x minus x1. Multiply through by 4, so 4y minus 8 is minus x plus 4. So x plus 4y minus 12 equals 0 is the equation of the tangent. Now, I'm not going to do the next part, the equation of the normal, because it's just repeating this process with a value of gradient of plus 4, so minus the reciprocal of this. Part C, explain why the domain is x greater than 0. So why does this function only exist for x greater than 0? And it's because when we look at our original curve there, we can't take the square root of a negative number. And although we can take the square root of 0, we can't divide by 0. So we're not allowed to have x having any value which is less than or equal to 0. After that, why every tangent has a negative gradient? Well, every tangent has this value, this this expression, and because we're only allowed to have values of x which are greater than 0, and because by definition the square root sign here is just the plus square root sign, that will be a positive number, that will be a positive. Top is always negative, negative divided by positive will always be negative. Now, explaining that succinctly is a whole nother ball game. So you might like to see if you get questions like that in the exercises.